The Titanic is still down there, in total darkness, silent, and for a moment it almost feels frozen in time. But here's the twist. It isn't frozen. The ocean is still dismantling it, right now. Rust-eating bacteria are slowly turning steel into dust. Every year something changes. A railing thins, a wall folds inward, a doorway becomes a jagged frame. So when people say, it'll be there forever, that's the lie. Tonight, in this deep sleep documentary, we'll gently tour 100 haunting rooms still inside the Titanic. These calm descriptions are not here to scare you, but to help you drift into a deep relaxation as we quietly witness what's still recognizable before it fades. Let the weight of the water settle over you. Let's begin with the first room. Start with something that feels engineered, not romantic. A watertight door track. These doors weren't scenery, they were a safety system. Each one was a thick steel slab designed to drop into vertical guides, driven by a mechanical linkage and held in position by heavy fittings that had to work under vibration, heat, and constant movement. Down here, the mechanism is no longer a mechanism. It's a set of corroding interfaces, rails, brackets, hinge points, and fasteners losing tolerance as oxidation eats away cross-section. You can almost picture how it worked when it was new, and you can also picture the failure path now. Thinning steel, weakened joints, metal turning to layered mineral and flake. From there, move into the boiler spaces, the ship's industrial heart. Even if you never see a perfect room, you feel the scale. Large cylindrical volumes, heavy plates, and the kind of structure built to contain pressure and heat. The Scotch boilers were massive, riveted pressure vessels, thick steel shells with seams, stays, and openings that once fed furnaces with coal. Today, silence replaces combustion, and silt replaces motion. But the engineering intention still reads: containment, reinforcement, load distribution. Corrosion doesn't care about intention, of course. It just reduces thickness until strength becomes margin, and margin becomes failure. Close by, the reciprocating engines are the kind of machinery people remember because of scale. They weren't small moving parts. They were towering assemblies of cast and machined components, with pistons traveling in controlled cycles, converting steam into rotation. Now, the motion is gone, but the mass remains, encased in sediment and darkness. The mind can still run the machine in imaginary slow motion, piston up, piston down, crank turning, bearings carrying load, and then you return to the reality that the ocean is gradually dismantling the same machine by chemistry, not by force. Then bring it upward into a corridor again, but not the first-class corridor you'd expect. Think of a service passage, narrower, lower, more efficient, built for throughput rather than comfort. These corridors are readable because they're pure geometry, straight runs, hard corners, repetitive frames. Underwater, geometry outlasts finish. What fails first are the thin edges, the fasteners, the seams, the places where stress concentrates and corrosion can start a crack line. Over years, the corridor doesn't collapse as a dramatic event. It loses stiffness, then alignment, then becomes an uneven channel where the original rectangle slowly rounds into ruin. Somewhere along that route, you pass storage and supply spaces, the ship's logistics skeleton. Shelving is often gone, but the anchor points remain: brackets, bolt holes, reinforcement where mass used to be stacked. Storage rooms tell you what the ship really was: a system built to move people, food, linen, fuel, tools, a floating supply chain. Down here, the supply chain is zeroed out. The room becomes a blueprint of function with the contents deleted, like an empty warehouse after the inventory has been erased by time. Now Let the material science show itself in a small, unglamorous room, a bathroom or wash area. These spaces are where different materials reveal their lifespans. Porcelain can persist. Thin metal fixtures often don't. Iron and steel convert into oxides and hydroxides through electrochemical reactions, and microbial communities can accelerate that conversion, building rusticles, mineral growths that feed on the iron compounds. Instead of rust, think of it as a steady reaction front moving through the metal, consuming structure from the outside inward. Next, a cabin, not because it's emotional, but because it behaves like a compartment, a small enclosure inside a larger enclosure. Once the soft layer is removed, textiles, paper, wood, you're left with the hard boundary. Corners, frames, partitions. Cabins are where you can imagine the exact moment a room becomes space. A seam opens, a panel drops, a boundary is breached, and the compartment stops being an enclosure. The ship is full of these threshold moments, and they're happening slowly, continuously. Then take the listener to a porthole, a simple engineering boundary that's easy to visualize. A circular cutout is a smart shape for stress distribution. It avoids the sharp corners that amplify cracking. But corrosion doesn't respect geometry. Over time, the frame loses thickness, fasteners weaken, and a clean circle becomes rough. The porthole used to be a controlled interface for light and air. Now it's an opening into black water, and year by year it becomes less a manufactured part and more a natural shape produced by chemistry. Now zoom out into a larger public volume, a room that depends on span. Big rooms need beams, supports, and connections that keep ceilings and bulkheads from sagging. As thickness reduces and joints lose strength, long spans begin to bow. You can imagine progressive deformation, first slight misalignment, then visible sag, then partial drop. Not a dramatic crash, a gradual redistribution of loads until something that used to carry weight no longer can. Finally, return to one more engineered interface, a doorway frame. Not the door itself, the frame. Frames tend to survive longer because they're integrated into the partition structure. Doors are components, frames are part of the system. Underwater, components disappear first and mounts remain. It's the same pattern across the wreck. Anything thin, movable, or lightly attached is sacrificed early. What's left is the ship's internal logic, the hard geometry of a machine being reduced, step by step, into mineral and sediment. Next comes the communication space, not because it looks dramatic, but because it represents a system. The wireless room was essentially an early communications hub, equipment that depended on insulation, dry air, stable power, and constant attention. Underwater, the signal is gone and the system is gone, but the mounting logic can remain. Where equipment was bolted, where wiring routes ran, where partitions separated heat and noise. It's like standing in an empty server room after the racks have been removed. The room still tells you what it used to do, even when the hardware is missing. Then you drift into a mail handling area, a room built for sorting and flow. Not luxury, not legend, logistics. Shelves, lanes, and working space designed to move items forward in time. Down here, paper and fabric vanish early, but the workflow geometry can still be inferred. Corners where sacks would stack, reinforcement where weight was supported, pathways kept clear for speed. It's an oddly precise kind of loss. The future-focused purpose remains visible, while the future itself never arrived. After that, imagine the scullery and pantry zones near dining, high-throughput rooms built around water in, waste out, surfaces clean, movement efficient. These are rooms where the design goal was repeatability. Underwater, repeatability returns in a different form, the repeatable chemistry of corrosion. Thin panels go first, fasteners fail, edges become brittle, corners trap sediment, and sediment holds moisture against the surface, accelerating the conversion of steel into rust layers and flakes. It's not chaos, it's a process running continuously at low speed. From there, you pass through a staff-only passage that feels more like infrastructure than interior design. Lower ceiling, tighter turns, less wasted space. These corridors were built to handle vibration, foot traffic, and constant use without complaint, which means that when they start to deform, you notice it clearly. A corridor is a ruler for alignment. When frames twist and seams separate, the ruler shows the error immediately. Down here, the ship is slowly losing straight lines. As stiffness drops, geometry sags, and the rectangle becomes an uneven channel. Then you reach a staircase or companionway that isn't famous, just functional vertical connection. Stairs in a ship are structural bridges between decks, and they reveal differential movement. When the hull settles unevenly, decks shift out of plane, and anything connecting them is forced to take shear and twist. Over time, those connections weaken. You end up with partial geometry, a few steps, a railing segment, a landing outline. It becomes a quiet map of how the ship has moved after the sinking, not in minutes, but across decades. Now consider a room that was built to manufacture a specific environment, the Turkish bath area. On the surface, it was heat, steam, controlled moisture, engineered comfort. Underwater, the environment flips completely. Cold, pressure, salt, and slow chemical attack. The decorative layer is deleted. What remains is construction, hard boundaries, tile fragments, partition shapes. It's a reminder that luxury is mostly environmental control. Remove the controls and you're left with materials, and materials behave according to rules that don't care what the room was supposed to feel like. Nearby, the swimming pool area becomes an elegant contradiction. A pool is water contained by structure, controlled water, bounded and safe. Now the containment is reversed because the room is filled with the ocean itself. The design intent is still readable in the geometry, edges, corners, the layout that once managed flow. But the ocean has taken ownership of the space, turning an engineered boundary into a meaningless line. It's one of the simplest ways to understand reclamation. The sea doesn't invade, it replaces. Then there's the gymnasium, a room built around machines, levers, pulleys, rotating parts, repetitive force. Underwater, motion ends permanently. Any exposed mechanisms seize, corrode, or disappear. What can remain is the footprint of function, bolt patterns, mounting points, the reinforcement where loads were transferred into the deck. It's like finding the anchor points of missing equipment in an empty workshop. A room designed to convert energy into movement now converts structure into sediment, quietly and continuously. After that, you drift through a public sitting room or lounge volume. On the surface, lounges are about comfort, but the engineering underneath is about damping. Soft materials that absorb sound, reduce vibration, make a ship feel stable and quiet. Down here, the damping is gone. The room becomes an undamped cavity, just boundaries, void, and gradual loss of edge definition. As joints weaken and panels detach, the room doesn't become scarier. It becomes simpler, and in that simplicity, you can sense the ship turning from engineered interior back into raw structure. Finally, move toward a damaged forward passage near break zones, where structural discontinuities are obvious. Broken load paths, missing supports, open compartments where walls used to distribute forces. This is where the slow motion part of your hook becomes concrete. As plates thin and frames corrode, sections can fold inward because the margins are already gone. It's progressive failure, not one dramatic collapse, but a continuous reduction in capacity until a wall that stands today sags next year. The Titanic isn't just sitting there, It's still yielding, quietly, mechanically, under the steady pressure of the deep. Now let's go deeper into the ship's utility layer, the spaces that existed to keep heat, light, water, and motion under control. Start with the coal bunkers, not a room in the hotel sense, but a storage geometry designed around mass. Coal was dense, abrasive, and constantly moved, which meant these compartments were built for load, not comfort. Heavy boundaries, tight access routes, and a layout that fed the boilers efficiently. Down here, the coal itself is long gone, but the logic remains. Where material would have piled, where shovel routes would have formed, where steel plates took repeated impact. Over time, the bunker becomes a quiet demonstration of attrition, abrasion, corrosion, and sediment gradually smoothing everything into softer edges. From there, imagine the firemen's working spaces near the boiler fronts, areas defined by heat management, airflow, and repetition. On the surface, these zones were loud and brutal: combustion, forced draft, constant movement. Underwater, all energy output is zero, but the architecture still reads as industrial. Tight clearances, access cutouts, reinforced boundaries where tools and bodies had to move quickly. It's the ship at its most mechanical, and now it's the ship at its most still, with the ocean replacing heat as the dominant force shaping the metal. Then come the uptake and ventilation pathways, the hidden routes that moved air and exhaust through the ship. You rarely see them clearly in wreck imagery, but they're important as an idea. The Titanic wasn't just rooms, it was circulation of gases, heat, and pressure. Those pathways were engineered gradients, flow from here to there, controlled by ducts, trunks, and openings. Underwater, flow still exists, but it's ocean flow, slow currents pushing silt into cavities, depositing sediment where airflow once moved freely. Over years, those channels become partially clogged, turning designed circulation into slow burial. Next, shift to the electrical side, the Dynamo room and adjacent spaces. Think of it as the ship's power plant, generators converting mechanical energy into electrical power for lighting, pumps, and communications. These rooms depended on dryness, insulation, and maintenance. Down here, insulation is meaningless and moisture is total. What remains is the industrial footprint: plinths, bolt patterns, heavy mounts, and the geometry of where machines once sat to resist vibration. It's another example of the same rule. Components disappear, mounts remain, and the room becomes a diagram of function without the function. From power generation, move to pumping and plumbing control, compartments where valves, manifolds, and pipe runs form the ship's hydraulic nervous system. A valve station is a calm thing to imagine. Turn, close, isolate, redirect. On the surface, it meant control over flooding, ballast, and water supply. Underwater, the irony is clean. Control systems are submerged inside the thing they were meant to control. Pipes become brittle, joints become weak points, and any dissimilar metal connections become chemistry experiments over decades. The room turns into a network of lines and junctions slowly losing definition, as if the ship's own veins are mineralizing. Then consider a refrigeration or cold storage area near the galleys, engineered cold inside a warm ship, created by machinery that needed power, seals, and constant operation. It's a useful contrast, because down here, everything is cold, but it's uncontrolled cold. The room that once maintained precise temperature becomes just another volume filled with seawater. The precision layer vanishes, leaving only structure, boundaries, racks, and reinforcement. It's a repeated theme: engineered environment versus ocean environment, and the ocean environment always wins by outlasting. Now, drift toward the galley and food prep zones. Again, not for nostalgia, but because they reveal workflow engineering. Kitchens are optimized for throughput. Stations, access lanes, storage placement, water routing. Even if every surface is gone, you can still imagine the layout as a system designed to minimize wasted steps. Underwater, the same layout becomes an erosion map. Corners trap sediment, narrow passages accumulate debris, and thin metal fittings are consumed first. It's like watching a factory floor slowly being erased until only the hardest boundaries remain. From there, pass into the bakery or pantry-adjacent prep spaces, rooms that existed to run reliably for days. Reliability is a mechanical concept, repeatable processes under load. Underwater, repeatability becomes chemical instead. Oxidation proceeds at a steady pace. Microbial activity builds mineral formations. Metal becomes layered, then flakes, then dust. It's almost meditative if you treat it as a slow equation. Given time, salt, pressure, and biology, structure transforms into sediment. Now, change deck level and go into third-class circulation. Corridors that were narrower, more utilitarian, less insulated from the ship's working vibration. These passages show how design changes with class, not as a moral point, but as a materials point. Thinner finishes, simpler partitions, different durability choices. Underwater, those differences can translate into different decay rates. Some spaces collapse faster because the margins were smaller, others persist because they're sheltered. The ocean doesn't judge, it just follows access and chemistry. Then step into a steerage cabin cluster, small compartments arranged for density. Compact enclosures make failure obvious. One partition yields and the entire room identity changes. These spaces were designed for basic shelter: a bed, a hook, a narrow walkway. Underwater, the bed and the hook vanish, but the compartment geometry can remain long enough to be recognized as human-scaled. And that human scale, inside an industrial wreck, is what makes the engineering feel real. This machine was built around bodies, not just steel. Finally, connect it all with a long internal route like Scotland Road, an extended service thoroughfare that functioned like an internal street. A long passage like that is a stability indicator. As long as it stays straight, the ship feels like a coherent structure. As soon as it warps, twists, or breaks, you're seeing the wreck's slow reconfiguration under pressure, corrosion, and settling. It's the Titanic as a structure still responding to loads, quietly, continuously, while the ocean keeps converting engineered certainty into mineral drift. Now shift to the ship's boundaries, places where the Titanic interfaces with the ocean through metal, glass, and seals. Start with the porthole rows along a passage. Repeated circular reinforcements cut into plating. Circles distribute stress better than rectangles, which is why engineers like them, but time doesn't care about good geometry. Frames lose thickness. Fasteners weaken. A clean circle becomes rough as oxidation advances. What was once a precise boundary for light and air becomes an uneven aperture into black water. And the repetition matters. Row after row, you can almost read the ship's original manufacturing rhythm in the spacing, then drift toward the windowed areas of public rooms, larger openings with heavier framing. Bigger openings require more reinforcement, and reinforcement means more interfaces, joints, riveted seams, brackets, and structural transitions. Transitions are where structures fail, because that's where stresses change direction. Underwater, these frames become slow-motion test samples. You can imagine load shifting as corrosion reduces thickness and joints lose capacity until a framed opening begins to distort. Not violently, gradually, the way a bridge sags when its stiffness is gone. Now consider a section of deck plating, the floor itself, and how it behaves over time. A ship deck is not just a surface, It's a plate system tied into beams and frames designed to distribute loads across a large span. Once a few supports weaken, the plate starts to dish. Once it dishes, it collects silt and debris. Once it collects silt, it holds moisture against itself and accelerates corrosion. The deck becomes a feedback loop. Slight sag to sediment accumulation to faster degradation to more sag. It's a quiet mechanical cycle that runs for decades. Move into the cargo handling spaces, hatches, coamings, and the reinforced edges around openings where heavy loads were moved. These are strong because they had to be. Reinforced edges are thicker, stiffer, and more resistant to deformation, which means they can persist longer than surrounding plates. Underwater, that creates an interesting effect. The stronger frames remain while weaker areas disappear, so rooms and openings start to look like empty brackets in the darkness, outlines of a ship rather than a complete ship. From cargo areas, drift to the chain locker and forepeak spaces, places built to handle extreme localized load. Anchor chain is brutal, heavy, abrasive, constantly shifting. The structure around it was engineered for impact and stress, which again means reinforcement, thick sections and strong boundaries. Underwater, you can imagine the chain itself lying still, but the environment keeps working on everything. Corrosion on metal, biological growth, silt settling into corners. A room designed for mechanical violence becomes an oddly quiet chamber, still defined by its overbuilt strength. Next, move toward the bridge-adjacent rooms, not the bridge as a dramatic symbol, but the areas around it as an operations cluster. Navigation depended on instruments, visibility, communication, and power. Underwater instrument panels don't remain as panels for long, but the placement logic can. Where systems were mounted, where windows once framed the horizon, where partitions separated work from passage. It's another example of operational geometry lingering after components have been erased. Then take the listener down into crew quarters, compact rooms arranged for density and efficiency. These spaces are essentially human-scale modules. Their engineering signature is repetition, identical compartments, identical framing, identical routes. Repetition means you notice deviations, where one module collapses faster than its neighbor because it's closer to a break, closer to an opening, or more exposed to current. The ship becomes a field of experiments. Same design, different environment, different outcome. Now consider the galley exhaust and ventilation trunks again, but this time as structural voids that act like pathways for water movement. Any void becomes a conduit. Any conduit becomes a current path. Currents transport silt. Silt buries openings. Buried openings trap moisture and accelerate local corrosion. So the ship's internal air system becomes an ocean system, a slow set of flows shaping the wreck from the inside, not with force, but with persistence. From voids, move to the idea of the ship's central longitudinal strength, the internal framing that helped the hull resist bending in waves. The Titanic was designed to handle hogging and sagging loads at the surface. On the seabed, the loading changes. The ship is supported unevenly, sections settle at different rates, and corrosion reduces the ability of frames to share stress. Over time, the structure behaves less like a continuous beam and more like separate segments with weakened connections. That's when you get slow shifts, slight twists, incremental settling, and progressive loss of coherence. Finally, end this set with a simple, stable image, a long passage that still holds line, a corridor that remains straight enough to feel engineered, because straightness down here is temporary. As soon as stiffness drops below a threshold, geometry starts to wander, frames deform, seams open. The corridor stops being a corridor and becomes an irregular channel. And that's the quiet truth running through every room in this documentary. The Titanic isn't preserved. It's undergoing a continuous mechanical reduction, steel to oxide, oxide to flake, flake to sediment, with the ocean doing what it always does, at the speed of deep time. Now we move into spaces where the ship's structure is easiest to read, because everything is simple and heavily loaded. Start with the watertight bulkheads, the big transverse walls that divided the Titanic into compartments. A bulkhead isn't decoration, it's damage control engineered into steel. It's designed to limit flooding, distribute stress, and hold shape under shifting loads. Underwater, bulkheads become long-term endurance tests. Corrosion reduces thickness, joints weaken at seams and brackets, and any opening in a bulkhead becomes a stress focus. Over decades, you can imagine the bulkhead transitioning from rigid boundary to flexible panel, still standing, but no longer providing the same structural certainty. From bulkheads, drift to the door cutouts within them, the engineered compromises. Every opening is a trade, accessibility versus strength. Frames around openings were reinforced, but reinforcement means more interfaces, more fasteners, more seams, and seams are where corrosion can concentrate. Under pressure and time, the opening edges become rounded and irregular. It's a slow erosion of precision. A doorway that once fit a door tightly becomes a jagged outline as the metal loses its clean geometry. Next, consider the stairwell shafts again, not as stairs, but as vertical load pathways and voids. Vertical voids act like channels for water movement and debris transport. They also reduce rigidity, because they remove continuous material from the structure. When surrounding supports weaken, shafts become collapse zones, places where geometry fails first because there's less material to carry load. The ocean doesn't need to push hard. It just needs time to remove enough thickness until the structure can't hold its own shape, then move to the ship's outer shell plating, the hull skin. Hull plating was riveted in overlapping strakes, designed to handle wave loads, impact and vibration. On the seabed, the hull becomes an interface under constant chemical attack. Rivet lines and lap joints are natural weak points. Crevices trap sediment, hold moisture, and accelerate corrosion. Over time, the plating doesn't tear like paper. It thins, softens, and loses continuity. Once continuity is gone, stiffness collapses and the hull begins to deform under its own weight and the uneven support of the seabed. Now take the listener to the rivets themselves, small parts with huge consequences. Rivets are the ship's distributed fastener system, thousands upon thousands of mechanical joints carrying shear and tension. Each rivet is a point where stresses transfer. Each joint is a site where corrosion can undermine the connection. Over decades, the ship's failure becomes a joint-by-joint story. Not one big break, but a slow loss of fastening integrity until plates separate, frames lose their partners, and the structure starts to behave like disconnected panels. Then imagine a section where the deck meets the hull, a structural intersection. Intersections are where loads change direction. They're also where multiple materials, seams, and attachments come together. Underwater, intersections become problem areas. Crevice corrosion, trapped silt, and repeated micromovements as the wreck settles. The result is gradual loosening. A joint that once behaved like a single continuous structure starts behaving like a hinge. Next, move into a cargo hold void, a large interior space designed to carry heavy mass low in the ship. Holds are simple: big volume, strong boundaries, reinforced edges around access points. Underwater, big voids become sediment collectors. Silt settles, debris accumulates, weight increases, and as that weight increases, the supports beneath it work harder, while corrosion is reducing their capacity. It's another feedback loop. Accumulation adds load, while chemistry removes strength. Now drift toward the hatch covers and coamings again, the reinforced lips around openings. Coamings persist because they're thick, stiff, and designed to resist impact. In wrecks, you often see this pattern. The robust frames remain while the thin plates around them disappear. The ship starts to resemble a skeleton of strong edges. It's not dramatic, it's mechanical. The ocean is selecting for thickness and reinforcement, the way a grinding wheel selects for hardness. Then consider the idea of the ship's internal longitudinal framing, the spine effect. At the surface, the Titanic had to resist bending under waves. On the seabed, the wreck experiences uneven support and long-term settling. Sections sink into sediment at different rates, and as connections weaken, the ship stops sharing stress effectively along its length. That's how coherent structures turn into separate segments over time, not because of one moment, but because the load-sharing network quietly fails. Finally, end this set with a simple operational space, a pump room or valve access area. Even if the equipment is gone, the pattern remains. Pipe routes, mounting pads, flanges, access clearances. These rooms represent control, isolate, redirect, manage water. Underwater, it becomes the clearest irony on the ship. The room built to manage flooding is permanently flooded, while its metal parts are slowly being converted into minerals. And the process continues without pause. Steel to oxide, oxide to flake, flake to sediment, the Titanic systems becoming geology. Now move into the ship's vertical systems, the shafts and trunks that connected decks, moved heat and routed people. Start with an elevator or lift trunk area, not as a luxury detail, but as an engineered void. A vertical opening removes material that would otherwise carry load, so it has to be framed and reinforced. Underwater, that framing becomes a long-term stress test. As corrosion reduces thickness, a reinforced void can turn into a collapse initiator. The surrounding structure loses stiffness, edges deform, and the opening slowly widens into a larger failure zone. It's the kind of change that happens quietly, with no sound, because water absorbs everything. From there, drift into a ventilation trunk, a designed channel for airflow that becomes a channel for water movement. Any trunk becomes a conduit. Conduits create current paths. Current paths move silt. Silt fills corners and holds moisture against surfaces, accelerating corrosion at seams and fasteners. Over time, the ventilation system stops being a system and becomes a set of sediment pipelines. It's a calm, mechanical transformation, air routing geometry repurposed into ocean routing geometry. Next, picture the ship's galley chimney uptake path, the root exhaust once used to rise and leave the ship. On the seabed, up becomes meaningless, but the void remains useful to the ocean as a space to circulate and deposit. Where heat once drove flow, now slow current and pressure differentials do. This is one of the most sleep-friendly ways to think about the wreck. The same channels still function as channels, just for a different fluid, under different rules. Then take the listener to a section of stair landing where multiple corridors meet, an intersection. Intersections are where structures accumulate complexity. More openings, more frames, more joints, more transitions in load direction. Transitions are where failure likes to start. You can imagine tiny, repeated stress cycles from settling and micromovement, combined with corrosion at crevices, gradually loosening the network of connections. The layout remains recognizable, but the precision slowly decays. Straight lines becoming slightly wrong, edges becoming softer, seams becoming gaps. Now move into a mechanical workshop space, a fitters or engineers area where tools and spares were stored. Workshops are designed around work surfaces, storage, and clearances for heavy parts. Underwater, the tools are gone, but the room's industrial logic can remain. Reinforced corners, mounts for benches, brackets for racks. It's another example of function surviving as geometry. The ocean deletes the inventory, but it leaves behind the map of how work was done. From workshops, drift to an auxiliary machinery compartment, not the main engines, but the supporting equipment, pumps, compressors, generators, and the plumbing that linked them. Auxiliary spaces were built to be serviceable, which means access lanes and mounting pads are often clear. Underwater, mounting pads can outlast the machines, leaving a pattern of bolt holes like footprints. It's like reading a factory floor after the equipment has been removed. You can still tell where vibration mattered, where weight was supported, where forces were transferred into the structure. Next, take a calm look at pipe runs in a passage. Long lines of metal that once carried steam, water, or compressed air. Piping is a perfect place to think in engineering terms because it's all interfaces. Joints, elbows, flanges, clamps. Every interface is a potential weak point. Over decades, the weakest interfaces fail first. Sections detach, and the line becomes fragmented. What was once a continuous system turns into isolated pieces, like a broken circuit. The process is predictable. Thin sections go, fasteners go, then the remaining segments become debris that settles into corners. Then move into a room defined by insulation and heat shielding, a place that used to manage thermal gradients. On the surface, thermal management keeps materials within safe limits. Down here, thermal gradients are basically gone. Everything is cold and steady. But the consequences of heat management remain. Layers that were once attached, wrapped and sealed, are now missing, leaving attachment scars and bare surfaces. It's an important idea for the male, technical tone. The ship was a controlled environment. The wreck is an uncontrolled environment, and the difference is visible in what disappears first. Now, drift toward a long, straight passage again, because long passages are stability indicators. As long as a passage holds line, the ship feels coherent. When it starts to bend, twist, or break, you're seeing the moment the structure stops sharing stress effectively. In a slow time lapse, it's a shift from one machine to several segments. The corridor becomes a measuring tool. It tells you when rigidity is leaving the system. Finally, end this set with a simple boundary detail, a handrail or metal edging that once guided human movement. Handrails are thin, exposed, and attached at intervals, which makes them perfect indicators of corrosion. They don't fail because of dramatic forces. They fail because cross-section disappears until there's nothing left to carry even small loads. Year by year, rail segments vanish, and what used to be a clean line becomes discontinuous. It's a quiet proof of the core idea. The Titanic isn't staying there. It's being reduced steadily by chemistry, pressure, and time. From here on, we'll slow down even more. We've looked at the Titanic like a system. Compartments, load paths, corrosion. Now we'll take a quieter walk through the same structure at human scale. Corridors, cabins, thresholds. Same physics, just closer to the rooms people actually touched. Now move to the simplest kind of evidence, a section of deck grating or metal tread where traction mattered. On a ship, surfaces are engineered for friction. Patterned plate, ridges, grates, because wet steel is unforgiving. Underwater, the traction pattern becomes a corrosion indicator. The raised edges thin first, the pattern softens, and once the pattern loses definition, you're watching cross-section disappear in real time, just at deep time speed. A surface built to keep people stable becomes a surface being steadily erased, then drift to a hinge line, not the door, but the hinge geometry itself. Hinges are small, but they're the definition of interface engineering. Pin, knuckle, bearing surface, fastener. Under constant salt exposure, pins seize, bearing surfaces roughen, and the connection stops being a connection. What remains is the outline where motion used to exist. It's a clean way to think about the wreck. The Titanic is full of joints that once moved, and now every moving joint has become a fixed, corroding interface. Next, picture a run of pipe hangers along a bulkhead. The pipe may be gone, but the hangers often tell the story. Repeated clamps at regular spacing, each one a designed load point. Hangers fail when fasteners thin, or when the pipe mass shifts and torque increases at the attachment points. Over time, lines detach in segments. First one clamp goes, then two, then an entire run falls and settles into silt. It's predictable structural behavior. Distributed support becomes uneven. Uneven support becomes overload. Overload becomes separation. Now let your mind settle on a valve wheel, a simple control element. Open, close, isolate. A wheel is human-scale engineering. It fits a hand. It trades leverage for control. Underwater, the wheel is still recognizable because the geometry is honest and durable. But the stem and internals are where corrosion does its work. Threads lose definition, seats degrade, and the valve becomes permanently irrelevant. Control systems don't fail dramatically, they just become meaningless once the environment exceeds their design envelope. From valves, move into a section of cable trays or wiring routes. Even if the cables are gone, the routing logic can remain. Brackets, clips, penetrations through partitions. Electrical systems depend on dry insulation and predictable paths. Underwater, insulation is erased early, and copper, steel, and fasteners each age differently. What's left is the skeleton of routing, and it quietly reminds you how complex the ship was. Light, power, communication, all reduced to empty mounting points and corroded attachment scars. Then picture a watertight penetration where pipes or cables pass through a bulkhead. These penetrations are engineering compromises, a hole in a boundary that must still behave like a boundary. On the surface, seals and glands handled it. Down here, seals are long gone, and the penetration becomes a weak point where corrosion and movement concentrate. Over time, the neat circular opening turns irregular. The edges thin. The boundary loses its clean function. It's the same story repeated. Interfaces fail before plates do. Now drift toward a ladder well or vertical access trunk, a utilitarian route meant for maintenance and quick movement. Vertical routes are vulnerable because they combine openings, framing, and load transitions. When nearby structure loses stiffness, the well can distort. When it distorts, attachments detach. When attachments detach, debris accumulates. These wells become sediment funnels. The ocean uses them as pathways, moving fine material into places that were never meant to hold it, slowly adding weight while corrosion removes strength. Next, move into a toolroom footprint, the place where spares and hardware were kept close to machinery. You don't need the tools to imagine it. The room explains itself through reinforcement and layout. Where heavy parts were stored, floors were strengthened. Where benches were anchored, bolt patterns remain. A workshop is function made visible, clearances for lifting, routes for carrying, mounts designed to resist vibration. Underwater, the work is gone, but the engineering discipline remains as geometry. Then take the listener to a shaft tunnel concept, not necessarily visible as a tunnel, but as the idea of a long protected route for rotating power transmission. Shaft lines require alignment. Alignment requires rigid supports and predictable bearings. In the wreck, alignment is what time attacks. Supports corrode, bearings seize. Settling introduces misalignment. A system designed to rotate smoothly becomes a static line that tells a story of shifting loads and lost tolerances. Even without seeing the shaft itself, you can imagine the precision it demanded, and how the ocean gradually removes precision from everything. Finally, settle on a section of railing stanchions, the posts more than the rail. Rails are thin, stanchions are thicker and attached to structure. That's why you often see posts remaining after lines disappear. Each stanchion is a small cantilever. It depends on a base connection that must resist bending. As corrosion reduces the base thickness, the stanchion's strength drops until even small forces, settling, current, its own weight, can tip it or detach it. Year by year, lines become gaps, gaps become absence, and the ship's clean edges become discontinuous. Now move to a manhole cover or access plate, the kind of circular or oval hatch used for inspection and maintenance. These covers are engineered closures: a rigid plate, a gasket surface, a bolt pattern that distributes clamping force evenly. Underwater, the gasket is long gone, but the geometry stays readable. The bolt holes often survive as a perfect ring, even as surrounding metal thins. It's a quiet marker of precision, a place where someone once needed repeated access, now sealed by depth and time. Then drift to a flange joint on a pipe run, two faces brought together, aligned and tightened with bolts. Flanges are clean engineering: alignment, compression, sealing. They're also natural corrosion sites because they create crevices. Crevices trap sediment, hold moisture against the metal, and accelerate localized attack. Over decades, the bolts lose cross-section, the faces separate slightly, and the joint stops behaving like a joint. The pipe becomes two pipes. Systems become segments. That's the Titanic in miniature. Distributed networks slowly breaking into disconnected parts. Next, picture a steamline elbow, a simple bend that once handled heat, pressure, and vibration. Elbows concentrate stress because they redirect flow and load. They're also where supports often change spacing. Underwater, an elbow can become a tell for structural history. If an elbow remains, it suggests the surrounding supports held for a long time. If it's missing, it suggests a chain of failures: hanger loss, torque increase, and eventual detachment. It's all about load paths. Remove one support and the stress migrates until something else gives. Now move to the idea of a deck beam row, the repeating structural ribs beneath a deck. Beams are what make a deck a system rather than just a sheet of plate. They distribute weight, resist bending, and keep surfaces flat. Underwater, once corrosion eats enough thickness, beams lose stiffness and the deck above begins to dish and sag. When it sags, it collects silt. When it collects silt, it gains load. The cycle repeats. It's a calm, mechanical feedback loop that slowly converts engineered flatnesses into a sediment bowl, then drift into a broken partition edge where thin internal walls once separated rooms. Partitions weren't meant to carry major structural load, but they contributed to rigidity and compartment behavior. As they weaken, rooms stop being rooms and become open volume. You can imagine the failure sequence. Fasteners corrode, panels detach, and the boundary collapses into fragments that settle. It's less about drama and more about topology. The ship's interior is slowly losing boundaries, and with each lost boundary, the wreck becomes more like a single connected cavity. Next, follow a hand crank wheel or mechanical control point, something designed to be operated without electricity. These are the most human pieces of engineering: leverage, gearing, force multiplication. A wheel implies torque, a crank implies repeated cycles. Underwater, these controls remain as shapes, but the internal reality changes. Threads seize, gear teeth pit, shafts lock. The control still looks like control, but it's control over nothing. It's a useful idea for sleep. The shape remains while function dissolves. Now move into the ship's plumbing manifolds, the cluster points where lines split, merge, and change direction. Manifolds are dense with joints. and joints are where time concentrates its work. Every junction adds fasteners, edges, and crevices. Underwater, those crevices become corrosion accelerators. Over decades, a manifold can degrade faster than straight pipe because it offers more surfaces and more interfaces. It's the same rule repeated: complexity is fragile, simplicity lasts longer. Then picture a ladder rung section or a short piece of access ladder still attached to a bulkhead. Ladders are engineered for human weight and repetitive use. Each rung is a small beam. Each attachment is a shear point. Underwater, attachments thin until the rung becomes a lever acting on a weakened base. Eventually, a rung detaches and becomes debris. The calm part is the predictability. Any repeated, thin structural element will follow the same trajectory: thinning, loosening, separation, settlement. Next, consider the interface between steel and wood, places where wood paneling or decking was fixed onto metal structure. Mixed material interfaces fail early because one material disappears while the other remains. When wood is gone, you're left with attachment scars, bolt holes, nail patterns, bracket outlines. Those scars are a blueprint of interior finish that no longer exists. Underwater, the ship becomes an X-ray of itself. Finishes removed, attachments exposed, the underlying structure finally visible. Finally, settle on a threshold plate, the metal strip at the base of a doorway, designed to handle wear from footsteps and moving loads. Thresholds survive longer than surrounding finishes because they were built for abrasion. Down here, abrasion is replaced by corrosion, but the principle is the same. The thicker part persists while thin edges vanish. Over time, thresholds become isolated fragments, small islands of durable metal that outlast the rooms they once connected. And that's the long, quiet pattern the ocean keeps repeating: reduce, separate, settle, until the ship is no longer a ship, just a field of mineral and shape. Tonight, we've moved through the Titanic the way an engineer reads a structure. Compartments, joints, load paths, and the slow chemistry that turns steel into sediment. Nothing down there is truly still. Even in total darkness, the wreck is changing, one interface at a time. If you're still awake, let your breathing slow. Let the pressure of the deep feel distant and steady. And if you've already drifted off, that's exactly the point. Good night.